Welcome to Differential Equations, Section 3.7. The problems we're looking at today are ones you might find in a physics course or in an electrical engineering class. So, in problem 1, we have an RL circuit. I have an inductor of 9 henries. I have a resistor of 63 ohms. The switch has been in position 1 for a long time. E in that time was 504 volts, and it's been there for a while, so it's come to equilibrium. So we now move the switch to position 2, which takes E out of the circuit, and so the question is, what's going to happen? So here's our model. My inductor times I prime plus Ri is E, but since there is no E, it's 0. Divide through by 9. This is an easy first order problem to solve. And so I get CE to the minus 7t. Plug in our initial current of 8. And I see that C is 8, and so I of t is 8e to the minus 7t. And if I look at the graph, you see here we are at 8, but it very quickly decays, and so I of t is quickly approaching 0. All right, if I'm looking here at problem 2, similar situation, have a switch, have our voltage source E. In this case, E is a decaying trig function, so it's decaying out. I have a resistor of 20 ohms, inductance of 2 henries, and so we form our equation. So first order, here's our driving function. I can at least reduce it and divide things by 2. And so we get this first order problem. Way back when we were looking at first order problems, we had integrating factors. And my integrating factor here is e to the 10t. So if you remember what that meant was we multiplied both sides by that, and that was the derivative of this product. To get rid of the derivative, we integrated. All right, easy enough. I'm going to divide by e to the 10t. All right, so integrating this, I get a sine 60t. I get a 1 over 60 in the front. I get my constant on the end, which is also divided by e to the 10t. All right, so I get my basic solution. And so now if I plug in I at 0 is 0. All right, I find it that what that means is, so the sign is 0, that's missing. And e to the 0 is 1, so C must be 0. And so here's my current over time. So it is oscillating, but the amplitude is being mitigated here by this decaying exponential. And so if we look at the graph of this, you can see it quickly bumps and then decays very quickly. So the negative exponential is modifying the amplitude from both sides. All right, if we look at an RLC circuit, and I'm looking at the current, what we get is a second order differential equation where I've got my inductor, my resistor, my capacitance, and the right hand side is the derivative of whatever your voltage source is. So in our case, voltage source is 50, and so its derivative is 0. I'm plugging in my inductance, my resistance, my capacitance. 1 over this number is 80, and then I'm going to divide through by 4. And so we get a second order problem here. Form the characteristic equation. Use the quadratic formula because it's not factorable. I notice the thing under the radical is negative, so I'm going to get complex roots. And so my basic answer for the homogeneous one looks like the following. Now, I know that my current at 0 is 0. Well, let's see. So at 0, this whole term is missing. Cosine of 0 is 1. E to the 0 is 1. So I get C1 is 0. All right, so we've reduced the problem now down to this. All right, so let's see. I need to find I prime. So I differentiate this. It's going to be a product rule, so it looks like this. I need to find I prime at 0. Well, sine of 0 is 0. This is a 1, that's a 1, and so I get at times 0, I get 2c2. So hold on to that thought. Now let's go back to some basics for our particular problem. We have plugging in L, R, my 1 over C. They told us what the charge initially was. E at 0 is 50 because we had a constant voltage source. And so if you start solving for this, you find that I prime is going to be, or 4I prime is minus 400. So I prime at 0 is minus 100. But remember from above, that was 2c2, which gives me that c2 is minus 50. And so here's what the current will look like. It is oscillating, being modified by this negative decaying exponential. This means that my current's going to bump quickly minus. And so let's take a look. So yes, it does. It bumps minus quickly and then decays back down towards 0. All right, in question 4 here, we have an RLC circuit. So I've got my basic equation here. So here's my basic equation. My voltage source is 150 cosine 2t. But remember, in the basic equation, I need V prime. So the derivative of this is my minus 300 sine of 2t. And so now I start plugging in what I know. Capacitance is 0.02. 1 over that is 50. Notice they're also giving me the charge at time 0, which we're going to need later. All right, so I start looking at my basic problem. So here's the basic problem. All right, at time 0, it's 0, so that's given. I look at the basics that we know. So E of 0 is 150, and I grind through all of this. And I find I prime at 0 is 0. We're going to need that soon. All right, so back to my homogeneous problem without the driving force, so equal to 0 here. Form the characteristic equation. Doesn't factor, use the quadratic formula. I've got complex roots, and so here's my homogeneous solution. All right, so let's see. Because of the driving function we had, I am assuming it's going to be of this particular form. All right, so looking at that, so looking at my problem, so here's our driving function. And so I'm looking at that and I start solving all of that, matching up coefficients, and I get some equations to solve, two equations and two unknowns. And we finally get what IP would look like. And so my full solution has the homogeneous one. It's got the solution from my guess where we found the coefficients. And looking at this stuff in here, I can figure out, because I at 0 was 0. So looking at the parts that are 0, sine is gone. Only the cosine parts are 1. So that's where this came from. And so I can find C1. So now if I know C1, I can find I prime. All right, so a bit of a work to get there. So looking at that, we know from before that I prime of 0 was 0. So this part here, how I know that is from before. And now I'm matching it up with this part. And that's how I get that C2 is minus 30 over 17. So putting all this together, I've got my full current solution. All right, I've got this piece which is transient, meaning it's going to decay very quickly, but initially has an impact. And then over a little bit of time, it's going to go into the steady state for the current. And so I plotted some of that. So that's just how we are looking. All right, and then I said, okay, what if I just solve the whole problem using Wolfram Alpha? How would I do that? Well, you just say solve. You just fill in the information we have from our basic setup, the stuff that we know about the initial current and the initial derivative of the current. So I did that. And so it solves the problem quite quickly for what the current would look like. And then I used alpha again to make a graph of it so I can take a look at this thing. So I just said plot. And so the way I did it is I just clicked on the answer. Alpha automatically put it in a window that could plot it. And so I said plot it from t equals 0 to 8. And so when I look at that, what you can see is I at 0 is 0. This is the little transient portion, but very quickly notice it goes into the steady state solution. So kind of some interesting problems. So again, use your tools. Don't just, the concepts are what is important, not grinding out all the algebra. So use some tools to help you really see and visualize what's going on.